By the way. So, okay, let's roll. Let's roll. Yesterday we left off at this point. Vilma, you need this from yesterday. We left off at electron configurations. So we had just finished this big old chart. So if I ask you, what is the electron configuration for hydrogen? What would you say it is? 1s1. It is 1s1. The electron configuration for helium would be 1s2. 2 electrons, 2 electrons. Oxygens would be what? Do that one on your own. What oxygen be?
1s2, 2s2, 2p4.
I said do it on your own.
Let's see. Let's see.
Need my laser pointer. Oxygen has a total of how many electrons? 8. So it's going to be 1s2, 2s2, 2p how many? 2p4. And remember, up on our periodic table, everything here are s's. These are all what? D's. These are all p's, and these are my f's. F. Phosphorus. Phosphorus. Do that one really quick. On your own. Do electron configuration for phosphorus. Did you guys see that I posted the questions for the chapter on Google? Not as many this chapter. Some of those have multiple parts. So. You guys got it? Yes? No? Maybe so? Emily?
Yeah.
What do you got?
1s2, 2s2, 2p6, 3s2, 3p3.
1s2. 2s2, 2p6, 3s2, 3p3. Yes. Do you guys remember the off-ball principle? A-U-F-B-A-U. The off-ball said that the lowest energy level is filled first. So we always fill the lowest energy level first. And then Hund... Everybody remember what Hund said? You fill, he did say something, you fill the ups first. Hund said you fill the ups first. So if I was going to do an orbital diagram for this, or an off-ball diagram, 1s2, right? Here's Hund, yes, H-U-N-D.
Like a dog?
Isn't a dog a hound?
Yeah, but Hund, like in German.
I don't know what a Hund is.
Like in German.
Oh, got it. I mean, this guy might have been German. So my 1s2 orbital can hold how many electrons? 2. So the first one's going to go up. Second one's going to go down. My 2s2 orbital. Wow, I'm like writing dyslexic right now. Can hold how many electrons? 2. So 1 up, 1 down. My 2p6 orbitals, there are 1, 2, 3. So how would those fill? How would I fill these? Up, up, up. So I'd go up, up, up. And then my down, down, down. 3s2 is going to be an up, down. Leaving me my 3p3, so it's going to be 1, 2, 3 orbitals. And how are those going to look for my 3p3? Up, up, up. You got it. Hard one. Mercury. Do this one. Sweet only long one I'll make you do. We're gonna move on.
Oh, bruh.
Bruh.
All the way down there.
Hi.
Hello. Do you want us to do the alpha or like the electric?
No, just do electric configuration. I don't want the up downs for this. I'm not gonna have you do the up downs for something big like that. I'm gonna start mine.
If you write that wide, you'll have to take 2 lines.
I'm gonna take 2 lines, Joey. Oh my gosh. I feel like I'm being micromanaged right now. 3D10.
So you probably took up like a quarter of the page.
Took us half.
Oh, tragedy for you, I'm sure.
Yeah, I fell off.
And you guys know you can always check your work on these, right? How?
You just counted.
Count your little exponents, and those should all add up to what for Mercury? They should all add up to 80. Should all add up to 80. What comes after 6s2? 4f14. Don't forget your 4f14s. And then after your 4f14, your 5d10. So that's why we did that one. Cobalt. Why don't you guys do an orbital diagram for a cobalt? So I have 1s2. I'm going to give you the electron configuration. I want you guys to do the diagram. 2p6, 3s2, 3p6, 4s2, 3d7. So I want to see your ups, downs for cobalt. I want to see your ups, downs for cobalt. The good news is for our pictures tonight, it's going to be 55 and sunny. Which is pretty good for November 3rd. True. Wow, next week we're going back up to the 60s. Some good outside running weather. Are you still running? Every day?
Like twice a week.
Okay.
Sometimes once a week.
Better than me.
I'm not doing it at all.
So you're running as much as I am now. But you probably run way farther. I try to do 2 miles 2 or 3 times a week.
Oh no, I run like 1 mile once a week.
Oh,
I don't.
okay. 1s2, up, down. 2s2, up, down. 2p6, up, 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 down, down, down. 3s2, up, down. You guys see how we're filling one energy level at a time, right? That's the lowest energy level gets filled first. 3p6, up, 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 down, down, down. 4s2, up, down. And you don't have to draw the lines in between. I'm just showing you. 3d7, up, 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 down, down. Yes?
Can you explain that again?
Which part?
like, how do you know when they go up and down and when they just go up?
So each individual one is going to have an up-down, right?
Yeah.
So the s orbital only has 2 electrons, right? So for s, it's going to be 1 up, 1 down. Another s orbital, 1 up, 1 down. P orbitals have 3. There's 3 p orbitals. So it goes up, 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 down, down, down. Okay?
Yeah.
The d has 5 orbitals.
5, and then
So
it's
up,
like
up, 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 down, down.
7. Okay.
Okay?
Yeah.
Okay, cool. Short form. You guys remember doing the shortcut? The shortcut? Also known as the noble gas notation? Yes? So what would be the short form for cobalt? It would be AR 18 in brackets. Because remember, you go backwards to the previous noble gas. Because all of those were what? Full. All of those were full. And then we just show our outermost electrons then. So what am I going to do to finish this up? 4s2, 3d7. Where are my valence electrons located here? First of all, I will tell you that cobalt, and this is kind of tricky, has 2 valence electrons. My valence electrons are my 4s. How do you know? That's the highest energy level, right? So that's tricky. That's tricky. These, even though, and a lot of times you'll see this written actually as 3d7, then the 4s2. Either one's okay. I just like to do it in order with the periodic table, but you gotta know, those are actually your outermost electrons. Okay? Those are actually your outermost highest energy electrons.
What about when there's like when there's an S and a P?
What do you mean?
Like if there's like a 4s2 and then like a 4p6.
Then the 4p6 would be the highest.
But they both have the same like.
They do. If they're both the same, it's going to be the last one.
Okay.
It's going to be the last one. Here I've got a 4 and a 3, so it's going to be the 4.
We said that the lowest energy level fills first.
Mm-hmm.
For 3d7, is that technically a lower energy level?
That's why I'm saying this is your outermost.
Yeah.
But you draw like that, you just have to know.
Okay.
'Cause-
So the 3d isn't filled.
So the 3D is out there.
Yeah.
So this is going to fill first. The 4s2 is technically a lower energy level, but it's still the outermost. It's weird. It's weird. I just want to make sure you guys got that. Because AP Chem on these likes to do like little random things like that. Because electron configurations aren't hard, but they're going to be like, what's this little thing that's different? Brady.
Does that mean the D's and F's can never be the valence electrons?
I mean,
As they always follow?
usually you're not going to have a lot of valence electrons in your D's and F's. I don't want to say never, but yeah, that's a good thing to follow. Let's do another one. What would be the electron configuration for Ca plus 2?
Oh, this is okay.
So write the electron configuration for Ca plus 2.
I feel like that +2 means something.
Ah, must, yes.
Yes, that is correct. It is the charge.
I'm switching to pencil for this one.
Oh, going to pencil, wow.
Doesn't do that on
Well, what does plus 2 mean?
the charge.
And what does that mean?
It's the
It
loss.
has less to
It lost 2 electrons, right?
Okay, well then.
So we just don't count.
It's just.
So it's going to be 1s2,
It's great.
Oh, I think it's an electron. Oh,
2s2, 2p6,
not argon.
3s2, 3p6. This is essentially just argon, right? Because what does calcium want to do with 2 electrons?
Lose.
Lose 2. Once it loses 2, it's now like argon. That's how many electrons are full. So now try F minus. Electron configuration for F minus.
Just a minus one, right?
Minus 1. F minus 1. 1s2, 2s2, then what? 2p6. Because fluorine did what? Gained 1 electron. And now it's like neon. Now it's like neon.
Wait, so would the valence electrons be in 2s2 and 2p6?
These are my valence electrons.
How do you
Right?
know what they share?
It's the highest outermost energy level, right? So at fluorine, before I did this, it would have had how many?
7.
It would have had 7. So it's the highest energy level for
Okay.
valence electrons. Make sense?
Yeah.
My calcium would have been, before I did the 3p6, it would have had how many? Would have had only 2, right?
4s2.
Yes. 1s2, 2s2, 2p6, 3s2, yes. 3p6, because it lost 2. It would have been here. Yes? Wait, it would have been, hold on. 1s2, 2s2.
3p6, 4s2.
Before I did that, there would have been a 4s2, right? There would have been a 4s2. But I lost those 2. Yes? So those are my valence electrons. Okay, I'm going to make 4 electron configurations I want you guys to write down. The first one is 1s2, 2s2, 2p1. The second one is 1s2, 2s2, 2p2. The third one is 1s2, 2s1, 2p1. And the fourth one is 1s2, 2s2, 2p3.
Was that 2s2, 2p6?
Wait a minute.
1s2, 2s2, 2p2. 1s2, 2s1, 2p1.
There's something wrong here.
Something
1s2,
wrong here.
2s2, 2p3.
There's something wrong here.
Which electron configuration shows an atom in its excited / promoted state?
Got a raise.
Yes. Remember, one of these electrons got a race. And you guys caught it immediately, right? Which one is it? It's the third one. What did I do with my 1 electron that should have been a 2s2?
It went up
I promoted it up to a
to p1.
up to a p. You got it.
Can you promote it up to? So like, can you promote it to like a 2s or 3s1?
No. And we're going to talk more about promoting electrons in the future. Because there's going to be something that we're going to actually do with that. Shall we move to trends? I don't know why I asked you the question. Let's move to trends, is what I should have said. Because we have no option. We have to keep going.
The illusion of free choice.
Yes. I love how I'd like, shall I move to trends? It's like, what are you going to say?
No.
You could say no. Wait, Brady, can you go to the tacos thing?
What?
Did you get my email?
Oh, yeah, I think I can.
Okay.
Because Harrison and Kieran told me they nominated me for it, and I was like,
Yes.
you have to remind me 8 times, but yeah, I'll go.
Okay. Cool. Good? Can I flip my page?
Yeah, sure.
Okay. Periodic trends. We know all these.
I was so dejected about that.
We should already know all these, but let's talk about them. So periodic trends. Let's start out with the first trend, which is atomic radius / size. What are the 2 main things that affect periodic trends?
Is shielding a factor?
Number 1 is shielding. What is the other thing that affects periodic trends?
Is it what's in the proton?
It's the core charge, right? Or the distance from the core charge, right? So let's just say the distance from core charge. Or we could just say core charge. Those are the 2 main things. 2 main things. So atomic radius or size, as I am going down a group, does what? Do you guys remember what that does?
It increases.
It increases. As I move down a group, atomic radius size increases. Why? Number 1, what am I adding as I move down?
More shells?
I'm adding more shells / shielding. So number 2, my distance from the core charge does what? Increases. Is the core charge changing? The core charge is constant. Okay? And we're going to learn more about what the core charge exactly is on Monday and Tuesday.
Even though we're adding more protons, it's still constant.
Yes, because the core charge was a calculation to look at. I'm trying to think if I want to save this for later. Because we're going to do a whole thing on core charge. I'm just trying to think what order this would make sense to do it in. Let's keep going. All right, the core charge is constant. Core charge is constant. So if the core charge is staying constant, that means my net nuclear pull is going down. And if it's going down as I go down the group, what are my electrons going to be able to do? Expand. They're going to be able to expand. So core charge is constant. We're going to talk about what is core charge next week. But just know that that's not changing. Essentially, there's a calculation to take like your electrons in the inside and subtract your valence electrons, and it's the same. Because I remember last year I decided I was going to do this first and see if this makes what we're going to do Monday easier. What about as I'm going across the periodic table? What happens to my atomic size? Decreases. Why?
Well, the shielding effect is constant, but you're adding more protons.
I have the same amount of shielding. I have the same amount of shielding as I go left to right across the periodic table. This means my distance from the core charge is doing what?
Decreases.
No, it's constant.
It's constant.
Because it's the same amount of shielding, right?
Oh, yeah.
I'm not adding levels to make them farther away. So my distance from the core charge is constant. What is my core charge doing as I move across the table? What am I getting more of? It's increasing. My number of protons or core charge is increasing. Number of protons / core charge is increasing. Therefore, my net nuclear pull is increasing. I'm just trying to think if we want to keep doing this. I just need to think for 1 second if we should go out to the regular packet or if we should keep doing this. Oh, it's really quiet in here.
Not gonna last.
Hmm?
I said it's probably not gonna last.
I'm a little sleepy.
Also jacking off.
Let's keep going. Let's keep going. I think this is going to be best for our chemistry health. Second trend is ionization energy,
Okay.
which is defined as what?
The amount of energy it takes to remove an electron.
Energy needed to remove an electron. Energy needed to remove an electron. As I go down a group, what's going to happen to my ionization energy? Decrease. It's going to decrease. And a lot of these are just all the same thing. So as I go down the group, what happens? Number one, I'm adding more shields. I'm adding more shielding. Adding more shielding. Therefore, my distance from the core charge does what?
Increases.
Goes up. The distance from my core charge goes up. But as I go down a group, my core charge is constant. Therefore, the net nuclear pull, is going down. The net nuclear pull is going down, so it is easier to remove an electron. So it is easier to remove an electron. The farther away the electrons are, right, the less easily the nucleus can pull those in. It's easier to take them away. As I move across the periodic table, what happens to my ionization energy? Increases. My ionization energy increases. Because as I move across, same amount of shielding. At the same amount of shielding, therefore, my distance to the core charge is constant. My distance to the core charge is constant. As I'm moving across the table, my number of protons / core charge is increasing. Therefore, my net nuclear pull is increasing. So it is harder to remove an electron.
How much would it take to get an electron away from fluorine?
What about
A
neon?
lot.
Oh,
All right. Well, neon especially, right? Neon doesn't want to give anything away.
oh yeah, do the noble gases, like, how much does it take to take an
A
electron?
lot. A lot. It takes a lot. So those are my first two trends. The rest of them, I'm just going to kind of give them to you because it's all the same idea.
We're gonna write this down.
Yeah, I'll wait for you guys to catch up. Do you guys have like a little bit of room here on the right on your page? Yes?
I have more.
I do have room on the right.
Because electronegativity is kind of the same. Electronegativity
How can I use that?
is a new description for the same trend. Because electronegativity is just the attraction for a bonding electron. So this is the desire for an electron, which you would agree is going to be the same trend as ionization energy, yes? Because ionization energy is how hard is it to remove an electron, right?
Yes.
And this is saying how much does it want to gain an electron. So this trend is the exact same. As I move across, my electronegativity is going to increase. And as I move down, my electronegativity is going to decrease. Attraction for a bonding electron. It's the attraction for a bonding electron. Can I flip my page? Yes?
Yep.
I shall hydrate. What?
My water.
You're gonna be dehydrated for speech tomorrow.
And today.
The human body needs a lot of water.
I'm no different.
No, you're not.
I don't need water.
Promise you, you're not.
I only need Mountain Dew.
Do you drink Mountain Dew?
No.
I don't see you as a Mountain Dew drinker.
You like coffee.
I'm on the Mr. Heller mindset.
What does that mean? Can you
I'm-
explain that?
It's the Mr. Heller diet. I only drink Mountain Dew and I only eat Lurch's donuts.
Okay, I don't eat Lurch's Donuts all the time. It's mostly just the fair. And tomorrow is Fill Your Freezer Day. So, last day they're open. They have like all the flavors. Apple crisp, chocolate, cherry.
Where?
Out by Aldi. Their like original location.
Oh yeah.
The trailer.
I thought you were about to drink from this thing.
You know, water from U.S. sinks are mostly not contaminated. Unless you're in like Flint, Michigan. I
That's
think they fixed the pipe now.
true. I think that water's good to drink.
You said non-contaminated.
Yeah, you
Most-
said non-contaminated. That's good.
Most water from the sink is actually pretty nice in America.
Yeah, why would we? That's an advantage of living in the United States.
In Smithville, it's not.
In Smithville, it's fine. Does Smithville have city water, or is that all just wells? I don't know. I'm just not quite sure.
City water's icky.
We good? Okay. So the last couple trends are reactivity of metals. So if I'm talking about my reactivity of metals, as I move across the periodic table, well, what do metals want to do? Metals want to do what with electrons? Lose. So as I move across, is it going to be easier or harder to lose?
Probably harder because you gotta like.
Yes, my metals are less reactive as I move to the right because I've got more electrons that I have to lose, right? I'm increasing the amount. As I go down, it increases. Why? I'm adding more shielding. As I add more shielding, they can more easily lose an electron. What's up?
24, you got a grade anyway, right?
Yes,
Can she give you this? Because it's going to take you 3 more weeks.
I'm fine with that.
Okay.
Yep. Thanks. Thank you. Because as it goes down, as it's going down, I'm adding more shielding and they can more easily remove an electron. That's why francium is the most reactive metal on the periodic table.
Isn't there only like
Oh, those French.
isn't there only like
French
1 gram of francium like in existence?
Yeah, I don't think there's a lot. Non-metals is going to be the opposite, right? As I move across the table, it's going to increase. Because as I move across, non-metals want to do what with electrons? Gain electrons. As I move down, it's going to decrease. It's going to decrease. So my most reactive non-metal is francium.
Wait.
Wait,
Most
Sorry,
reactive
my most reactive non-metal is fluorine. Thank you.
Do these?
Because fluorine has very little shielding, right? It only needs to gain 1 electron, and those protons can pull them in the most easy.
Did this apply to the noble gases? The reactivity?
The noble gases aren't,
Oh, bullshit.
they aren't really going to do much.
Boring,
Yeah.
Yeah.
Something new, I don't think we talked about this last year, is electron affinity. Electron affinity, I know, it's fun, is the amount of energy released. The amount of energy released when when a neutral atom gains an electron. The amount of energy released, because we're going to be releasing energy when this happens. As I'm moving to the right, this is going to increase. As I'm moving down, this is going to decrease.
Does that say what a metal?
When a neutral atom gains an electron. So you might see something like this. X, some kind of gas.
What does it say?
The amount of
The amount.
energy, the amount of energy released when a neutral atom gains an electron. So you might see some kind of gas plus an electron yields an ion of gas. You might see an equation something like this. Or you could see, more specifically, here's my fluorine, which is a gas, plus an electron. That gives me F minus, which is a gas. And then you could see energy for this would be like negative 328 kilojoules per mole.
Also, does that say decrease down or?
Yes, decrease down, increase to the right. Last thing is ionic radius. Ionic radius, well, this depends on if it's a cation or an anion, right? If it is a cation, it's going to be what charge? Positive, because it did what? How do you become positive?
Lose an electron.
Because it lost electrons.
I was about to say be happy.
If I'm losing electrons, what's going to happen to my ionic radius? Decrease. It's going to decrease. The opposite will be true for an anion. An anion is a negative charge because it gained electrons. If I gain electrons, my ionic radius is going to increase. Why? Because if I have more like charges around the outside, what do those like charges want to do? Repel. They want to repel. They want to repel.
Oh, there's not no like atomic radius going, not ionic radius going across, or is it different because there's going to be both metals?
So it kind of resets, right? It kind of resets at group 16. Yes? Because at group 16, I go from losing to gaining. Or really group 15, I guess. Group 14 can go either way. So group 1, lose. Group 2, lose. Group 3, lose. 14 plus or minus can go either way. Group 15, gain 3. Group 16, gain 2. Group 17, gain 1.
Will the periodic table ever get too big to fill?
I don't know. It may. It may. I just have a feeling at some point we're just like going to discover like 20 more electrons or some new state of matter or something like that. Okay. Let's go back to the packet for the last 5 minutes. Let's go back to the packet for the last 5 minutes.
Is this going to be the end of the first set of notes in this?
For that, I might do one other thing later, but that's the majority for now. Because I remember last year, people said that I should do as many notes as I can before what we're doing Monday and Tuesdays. So we're going to see if what we're doing helps. All right, back to this. So on this, we left off here. We're back here. Using high energy, ultraviolet, or X-rays, photons, it's possible to eject, we talked about this yesterday, an electron from an atom. This is called the photoelectric effect. And is used to show, are we good now? It is used to show what we call photoelectron spectroscopy. Photoelectron spectroscopy, or PES. Photons that are used to eject electrons have energies calculated using the relationship between Planck's constant, H, which is 6.626 times 10 to the negative 34th joules times seconds, and frequency. And we know that H is going to be Planck's constant. That is also on the yellow cards. So that's not something that you have to have memorized. It is up there on H, on the third yellow card, up there. C, we talked about yesterday, is wavelength times frequency. So if we combine these two equations, because E is hv and c is wavelength times f, I can now say that frequency is speed of light over wavelength. This is all stuff we talked about yesterday. So the energy of a photon, combining all of these, is h, Planck's constant, times c divided by wavelength. H times c divided by wavelength.
H is 0 constants is the only thing changing is ever going to be the wavelength.
Yes. So this is what we're going to use. You can also calculate the energy emitted from promoting an electron if you know what energy level is promoted using this equation. Triangle E, your energy, is equal to negative 2.178 times 10 to the negative 18th joules times 1 over n F2. So that's going to be, what was my, so NF2? NF2, number, F2, over 1 Ni2. So what is that? Well, F is going to be my final, what number was my my electron promoted up to? So it's going to say like promoted from the first energy level to the third energy level. So F is going to be 3. This would be 1. This is just saying final minus initial. So this is going to be 1/3 squared. This is going to be 1 over 1 squared. It's a super easy equation.
So NF is all one thing.
Yes.
Oh.
So this is just final minus initial, both squared. If the energies exceed the ionization energy, they also add kinetic energy.
It's squared.
Yes, those are both squared. So HV is going to equal ionization energy plus kinetic energy.
Wait, that NF2, is that NF squared or NF2?
That's NF squared
Ah.
minus NI squared.
Oh, NF squared.
Yeah, so it's your final number squared minus your initial number squared. Whatever you started at for your electrons. This is what we are going to start with on Monday.
Initial energy.
HV equals ionization energy plus kinetic energy. Nice work today. That was a lot. That was a lot.
I'm gonna need to like process this for a half year.
That was a lot.
I love